Yeah, welcome to the first NCT Data Science Seminar in 2025. This event is jointly hosted by Heidelberg AI. A warm welcome to Katharina Breininger, our speaker, and to Annika Reinke, the host of today's event. It's my pleasure to hand over to you, Annika, for the introduction.
Thanks a lot, Doreen, for introducing the seminar. I have the honor to introduce our speaker, Katharina Breininger, for today's data science seminar. So let me talk a little bit about her background. She studied computer science in Marburg and Erlangen, and her PhD focused on image fusion during minimally invasive interventions in Erlangen and together with the Siemens Healthineers. Afterwards, she served as an assistant professor at the FAU in Erlangen-Nuremberg. And today, Katharina leads the pattern recognition group at the Center for AI and Data Science at the University of Würzburg. So her team and herself works on developing strategies and robust machine learning approaches for settings with small data in an interdisciplinary domain, but also with a focus on medicine and medical imaging. And today she will talk about a very relevant and exciting topic, often a bit frustrating. I think she will let us know about all the concerns and different challenges. It's about reproducibility of results in machine learning. So if you have any questions, feel free to use the chat or afterwards to interactively raise your hands and ask your questions directly. And now, Katharina, I am very much looking forward to your talk.
Thank you very much, Annika, for the very nice introduction, and thank you very much for having me here in the data science seminar. I'm very happy to talk today about reproducing machine learning results in, different contexts, but specifically trying to go from frustration to improving student education in this context. The work that I will be presenting in the next couple of minutes, in the next 45, hopefully, minutes is actually a joint idea together with Bernhard and Andreas Kist, and I'm presenting very intermediate and preliminary results. So see this as an evolving project that is still in the process of actually being fleshed out and being put into practice. So when I was invited and when I thought about the paper title, I actually thought quite a bit how to start this talk. So should I go back to my student code when I did my PhD and look for something where I wrote to-do documentation, next to the codes? Should I talk about the frustration that I had with different compiler versions and an error that I chased for weeks, or some paper that we recently tried to reproduce for actually publication at MICAI or submission to MICAI, and how it took us weeks to get to the same result? But then I thought, well, let's go a little bit more classic in terms of introductions and start with a quote. Here I would like to quote Joëlle Pineau, who a couple of years ago gave an extremely interesting keynote about reproducibility in machine learning. And I think today, more than ever, it is important to think about what we are as scientists and what we're trying to achieve. And here, science is a collective institution that aims to understand and that aims to explain. And given current circumstances, given current developments, I believe it is important to keep this in mind as we walk through the talk today. I'm certainly not going to deny that research can be competitive, that we're, chasing paper deadlines, that we're trying to get grants, that we're trying to get novel results and papers published. But at the same time, what we're trying to do seems to be completely in vain if we don't actually learn something from all of this experience, and if we are trying to reinvent the wheel again and again. Instead, the ideals that kind of underlines most of our research actually means that we dedicate a substantial part of our life to understand specific phenomena and to explain them to others. And accordingly, being able to learn from what people have done and to build on these experiences, to build on these insights, is an extremely important aspect of science. And here reproducibility really comes into the spotlight. I'm going to continue with actually two more quotes in this context that kind of come from this idea of reproducibility, or that try to define this idea of reproducibility a little bit better. Non-reproducible single occurrences are of no significance to science. From Karl Popper from 1934. Or we may say that a phenomenon is experimentally demonstrable when we know how to construct an experiment which will rarely fail to give us statistically significant results, from Roland Fischer, who many of you might know from, Fisher's t-test, etc. So what you can see here on the right is Boyle's air pump, which is one of the first elements of debate on reproducibility, basically trying to get the system working in different places of the continent of Europe, and then actually trying to show that results are reproducible, insights are reproducible, and machinery is reproducible. And while, of course, everything here has to be taken with a grain of salt, we can't expect a volcano to erupt whenever we want it. This idea of being able to reproduce and to define recipes that allow us to reproduce research results are extremely important. In terms of formal definitions, maybe we can disentangle this a little bit before we then ignore it for the rest of this talk to some extent. So when we talk about reproducibility, and I'm following here the definitions by Bolen and colleagues, reproducibility refers to the ability to duplicate the results of a prior study using the same materials and the same procedures. So this is more or less being able to do what other people have done with their data and with their approaches. A little bit more general is then the idea of replicability. Move the window out of the way. Replicability refers to the ability to duplicate the results of a prior study using the same procedures, but with new data that is collected, which is extremely important in the field that most of us are looking into, medical data science, right? So here we don't just want to work on the one data that we've extracted, but we want to generate translatable ideas and approaches. And then thirdly, generalizability refers to whether the results of a study also apply to other contexts, other populations that differ from the original application field. And here also many applications in data science for medicine where this is extremely important. And of course, there are many connections now where you can attach puzzle pieces to these initial definitions, and see this also as a hint to look into the other talks that you've heard in the data science seminar series. For example, the recent talk by Florian Markowitz. When we want to then walk towards translation, all of this again becomes important and adds just another level of complexity, but also of interesting research to the whole storyline. All right, so in the start of the 2000s and now going on, there has been this discussion about the reproducibility crisis in research. So basically a huge majority, you can see this here in this graph, the reddish colored area. Here researchers agree that there is a significant crisis, or at least a slight crisis, in terms of being able to reproduce research results that have been presented in scientific literature. And when we look here at a more fine-grained analysis of the different fields where people have struggled to reproduce experiments, we see actually that they are not that substantially different across different fields. So you can see here chemistry, biology, physics and engineering, etc. And interestingly, the trend stays the same. People also struggle to reproduce their own results, but even more so the results that someone else has reported. Now, computer science and machine learning is not directly mentioned in this list. The big question is, are we good? So are we fine in some way? And when we look at our research community, there are many efforts that try to foster reproducibility, right? We're proud about many things that generally work towards reproducible research results and being able to understand what is actually happening in different papers. There's the Papers with Code initiative that collects many research results on different levels and comparisons of state-of-the-art approaches. We heavily use GitLab and GitHub to share our code and to make this available to other researchers. We have numerous data platforms, including platforms like Grand Challenge, but also Kaggle, Zenodo, where a lot of our data is shared. And we also, in many cases, try to share models, so pre-trained approaches that can then be applied to different categories. At the same time, there has also been a rising number of publications that try to put a warning finger and try to put their finger in the wound of if this is actually what we have to do and how we get there to be able to reproduce results. I picked out one of them because I found it quite interesting, the replication crisis in our community. And I would like to zoom into this part here of the abstract and the introduction. So this is just an example, but they considered 18 algorithms, and out of these 18 algorithms, actually only 7 could be reproduced with reasonable effort. That is a really, really low number in this case when we proud ourselves in terms of being able to, just describe algorithms, and then you'll be able to do what we did before. But then, interestingly, and this is an additional problem that we have, out of these 7 methods, 6 of them were actually outperformed by very, very baseline methods and baseline approaches. So some part of the approaches that we present are not reproducible at all, and some just don't give the results that we would expect. And I want to put a little bit more power behind this statement. What you can see here are different approaches in terms of metric learning. And some of you might be familiar with contrastive and triplet learning as very basic approaches in this field. And then there has been a huge development. Let me just add here the laser pointer, a huge development, and different approaches have been proposed. What you can see here is really this nice trend, right? We have an increase in performance over the years. Now, the authors of this study looked a little bit deeper into a number of these algorithms and did extensive hyperparameter evaluations. And then, basically, with these optimized hyperparameters, they looked at the results again. And what you can see here, at least in this context, and just looking at performance and not much else, that there hasn't been that much of a progress in terms of, top 1 or precision at position 1. So this is a problem, right? So if this is what papers report, and if this is what happens when you actually look into the results, then there is a big question of how reliable the results are that we report in our research. And I think I'm talking here to a very open audience to this field. So there has been lots of work also from the DKFZ, from Lena Meyer-Heinz group on different topics. Also, Annika is working heavily in this field here. Just one bullet point or one spotlight out of that in terms of metrics that are used to rank challenge results for computational challenges, depending on the ground truth that is used, and if not, specific care is taken to have a very high quality ground truth, you can see the ranks just jumping up and down along the challenge participants here. Similarly, Fabian Isensee and the group at DKFZ has been working without pause to establish suitable baselines for segmentation, and the NNUnet is certainly one of the baselines that I will also mention again and again in the MICAI reviews that are just around the corner now. And 6 years after the introduction of NNUnet, there is still an ongoing innovation bias towards novel architectures. This is a quote from a very recent paper where Fabian and his colleagues identified several pitfalls that we see again and again in these scientific studies. For example, that claimed innovations are confounded with other performance boosters, and the comparisons are no longer fair in some way, that there is simply a lack of well-configured baselines similar to the metric learning results that we've seen before, that there is an insufficient quantity and suitability of datasets, the datasets that we use to benchmark our algorithms are not always suited for what we are trying to do. And then inconsistent reporting practices, non-standard approaches and evaluations make our lives further difficult. So this just basically as a bit of a motivation, we have this problem also. And it's not just something that chemists and biologists have to worry about when they are not able to, again, grow the cells on the medium that they have, or when they're dependent on very specific materials and to do their experiments. All right, so to just push this a little bit further, I would like to briefly talk about what causes we have for challenging and failing reproduction. So why is it actually so difficult to make sure that our results are reproducible? I've hinted at this in some points before, but I just want to give you here a little bit of a broader perspective. The first and very obvious thing is that reproducibility is limited by authors and companies by design for very different reasons. There might be commercial interests, there might be other reasons for keeping ideas to yourself in some way, to not spread your ideas too far. And I would like to give you the example of the recent GPT-4 model. So actually not that recent, but this is a very good example of where researchers by design decided not to tell people everything that they should know or could know about the method. And you can have different opinions about whether this is a good decision, a bad decision, a business decision, a policy decision, or whatever, but it is what it is in some way. And GPT still has a massive impact on the research community in large language models. And here the reason that they give is, on the one hand, the competitive landscape, so commercial interests, but also safety implications, policy concerns, and no further details about the architecture, hardware, training compute, dataset construction, training method, or similar are provided. So of course, if this choice is done by design, then it is extremely difficult to do reproductions, and people can just speculate and probe and see this as a whole new research question, how to get behind what is, how the mechanics are in this big machine. A second part that is closely connected with by design to some extent is data access. Data access is a huge topic, especially in the medical field, where data sets are very often specific to one institution, where they're private, where there are data security concerns or data safety, data privacy concerns. On the better side, there are also also platforms where you can ask for access and pay for access to specific data sets. But of course, this also limits the broad access and use of these data sets. So here I have the example of the UK Biobank, which is certainly a very well-structured system to get access to data. But here you have to go through multiple steps and have to pay to make sure that you get access to the data for a specific research proposal. So this is, I'm not judging, this is just a fact in a way that data access can be difficult. Especially huge data sets, often again for commercial reasons or for other reasons, are also private. Here the JFT3B data set, which is an internal Google data set, is not available to the public. And then even if we have large data sets, so here the Lion5B data set that is actually available to everyone, it's a whole different topic being able to work with data sets of this size. So it's not as if just a random research institution can decide to now start working on data sets that consist of 5 billion images. Similarly, in the domain that I'm working a lot in histopathology imaging, there is simply an infrastructure, a substantial infrastructure needed to be able to work with data sets that are that large and to be able to access data sets that have these dimensions. Which brings me to the next part. So hardware. Not everyone has every kind of hardware just at their disposal to be able to run experiments here. This can be extremely high-performing super computers, HPC clusters here. Capitan, I think it's still the #1 HPC in the world, but it can also be simpler in a way. So here, this is the HoloLens, which is now going, it won't be supported for a very long while in the future, but many experiments are running or are reliant on dedicated hardware and dedicated architecture. This is a little bit of a history lesson as well. So some time ago, the PlayStation 3 was actually used by multiple research institutes as research to form research clusters because they had very high-performing graphics units. But of course, this is not directly compatible to other research hardware or compute hardware that might be used in follow-up projects. So this can be a substantial problem as well, not being able to use the hardware that has been used and then dependencies to run on specific systems. Then, and I think this is a topic that many students can relate to, research code quality. So having code that has a specific characteristic in the terms of its usability for other persons and other researchers. So most research code is in a way prototype-based coding. So it's not as if we have this huge project or this huge product in mind and our code has to be a part of that. But in many, many cases, there is a prototyping process behind code development. Again, not judging. This is also the power that we have, that we are flexible, that we can implement new ideas very fast. But it also means that there are lots and lots of incremental changes, and very often this is done for a single user who has to be familiar with the code. I would call the second or this third point in a way documentation and test procrastination. So there is in many cases very, very imbalanced documentation and very imbalanced testing. So I've seen this for master and bachelor students again and again. If there's currently, a bit of time to procrastinate, let's add documentation and then not update that when the deadline is near and when the deadline is close and actually experiments have to be finished. Similarly, and this is something that we're guilty of as well, it might be that there is refactoring after experiments and after acceptance of a paper because you want other people to be able to use your code, right? But this changes, this can break dependencies, this can break part of the code that is actually responsible for specific results. So yeah, research code is can be a challenge to work with. And in addition to the code itself, there is the whole ecosystem that is behind that, including software versioning and issues that incompatibilities. Python is a programming language that allows for lots and lots of flexibilities, but that also allows for lots and lots of conflicts across the packages, that allows for actually platform independence, but still some things that just don't work across Linux and Windows systems, for example. And similarly, what we very often see, and this is in a way good practice, is that versions are marked, but then they're not marked for all of the parts of the project, which again then can cause lots and lots of issues if you're trying to install and to run repositories that have these descriptions. A next element that is frustrating, especially for students just starting in a specific field, is that we are a very rapidly changing research field. We have a rapidly changing common knowledge base, and there are just new and new ideas, new and new approaches that are established year after year. So I'm taking the example of diffusion models who have been on the rise now for a couple of years, and it might be easy to start with the initial papers, but then there are more and more recommendations and strategies how to successfully train these approaches. And not all of that might be mentioned in each and every specific paper. I mean, you have pH limitations, you have also this common knowledge understanding at some point that approaches, how approaches work and how implementations are standard. But this can be a big issue for people just starting in this field and can seem like a mountain where it's difficult to start somewhere. Now, everything that I've mentioned so far, I would say, is related to a fast-paced research field with resource limitations. But then there are also other aspects that we want to talk about, or that I want to talk about here. A very big issue in this context is p-hacking and hyperparameter optimization. If you just try often enough, you will get seemingly significant results. And this is something that we also see in many research studies as we try to replicate them. I've hinted at this before. Hyperparameters are an extremely important part of machine learning approaches. And here are just two choices and two comparisons, basically, where we have here different input sizes, or where we here have different activation functions, and they have a huge impact on the performance of these approaches. And not considering that, while reproducing approaches can lead to vastly different results and can lead to overconfident claims. And just as an example, or basically revisiting what I've said before, there are many, many pitfalls that students can fall in here, and that we as researchers can fall into. And while systems exist that, like the NNUNet framework, that help us to have more reliable baselines, this is not true for every field. This is not true for every research question. And even then, we have to be extremely careful not to fall into an accidental or even on purpose p-hacking problem. And of course, I also don't want to push away this idea of that there can be substantial problems in our research community. So one of the papers that I reviewed for this talk actually said reproductions are not that important because the probability of fraud is not sufficiently widespread to make it necessary. To be fair, this paper is now 15 years old, but our community has grown substantially, and the pressure that is on PhD students to publish at high quality conferences and in high quality journals is immense. We are dependent on research grants, and there is this pressure to produce substantial results. So thinking that scientific misconduct and fraud is not a part of some of the reproduction fails that we see would be naive from my perspective. So a multi-component system, in a way, that we have to consider when we look at reproducibility from a broader perspective. All right, so lots of negative things so far, lots of depressing problems that we see, but maybe we can look at this from a slightly different perspective. So we don't need to despair, but rather make a learning experience out of it. And here I want to talk about our efforts on establishing a hackathon and university courses to use the struggle with reproductions also as learning experiences. And here, this is much, much easier with lots of sweets, with lots of chocolates, and with wonderful collaboration partners like Bernhard and Andreas, who is making coffee here in the background, also extremely important in this context. So we started with this idea of diving into reproducibility as a project, as a problem, as a hackathon. And we started with the Reproduce CVPR hackathon in 2023. You can see here Bernhard Egger and Andreas Kist from the University of Erlangen-Nürnberg. Currently, they're working on extremely interesting fields in computer vision and also medical imaging. And this project is, I would say, the brainchild of Bernhard, and then supported by all of us in a way that we can leverage this at different institutions and on different levels. And the concept that we thought about would be to have a hackathon and then go beyond this idea of having a hackathon, leveraging the fact that CVPR papers have been public and available as open access publications since 2013. And we thought here about multiple stages. In the initial stage, we wanted to use this wealth of papers to do an initial analysis of papers and of code availability as the very fundamental requirement for easy reproductions in our fields using large language models. We then had the idea to continue this and to build on this initial analysis using a hybrid reproducibility hackathon in winter 2023 with PhD students, and then to use the insights that we have there to develop a university course for students in computer science, AI, data science, and medical engineering. And this is something that is currently in progress and where we'll be reporting some preliminary and intermediate results. And ideally, then in the next step, we would be able to profit from all the wealth and the knowledge that we acquired in these different stages. Now, I want to emphasize here that this idea is not completely out of the blue. We're standing here on the shoulders of the community in machine learning and computer vision, where I want to again highlight the work on reproducibility in machine learning and the ICLR workshop. The initial quote basically is centered also around this reproducibility workshop, which from the beginning also had the idea to integrate students in the reproduction of CVPR papers while they're being reviewed. ICLR papers while they're being reviewed. And then a fantastic initiative, reproducepapers.org, that also utilized reproductions as a means of teaching and did a broad evaluation of the benefits and shortcomings and challenges of reproducing papers in this context and for student education. So in the next few minutes, I want to talk about these different parts and these different stages and tell you a little bit more about our experiences. So stage one, the initial analysis of papers and code availability using LLMs. This is the result in a way. So you can see here the data analyzed by Fritz Schmidt, a student of Bernhard's, separated into different parts. And we can very, very nicely see here that the number of papers submitted to CVPR over the years has grown quite substantially. What you can see here in green are the papers where we are pretty sure that there is a decent code base available. There is a link in the GitHub repository, and there are some fundamental requirements towards a Git or a similar project page repository that allow us to say, okay, we don't know about reproducibility yet, but at least the code seems to be in a decent state. For the blue papers, there's code promise, but we weren't able to find any link. It might be added later somewhere on the web, but it's not contained in the paper. And then for the orange ones, links were in there, but our large language model was not powerful enough to discern whether this was actually suitable, if it was a paper, basically a reference approach or something similar that was also just integrated here. So the green ones are kind of the gold standards in some way, and the orange ones potential, but we're not sure, and definitely some inconsistencies in the way that these results are presented. If we look at this from a percentage base, it looks a little bit more depressing, to be honest. So we can see here that the green part and the percentage of papers that have code available in a somewhat standardized format actually pretty much stagnates since 2017, despite lots and lots of efforts to provide reproducibility checklists, to establish best practices, etc., etc. So yeah, there apparently an easy identification is still not possible, given there are lots and lots of limitations with our LLM-based analysis. But I think it's safe to say that for all orange papers, additional steps might have to be taken to discern whether code is available in the way that we would like it to be available. So we do see here an increase in the orange part, percentage-wise, as well. And it will probably cause us quite a bit of interest and research effort to disentangle now whether there is potential there for better reproducibility, or whether people just add more GitHub links to their papers in some way. So based on this, we were pretty confident that there was at least a subset of papers available for suitable reproduction, and a lot of interesting papers to analyze in more detail. So we went on to stage 1, the hybrid reproducibility hackathon in winter 2023. And to be honest, it was awesome. I can't put it differently. We had 4 days of coding, of scientific exchange, of food. We had more than 40 participants, both online and in person. We were still a little bit touching the COVID pandemic, so that was maybe the negative part about that, but generally it was a really vibrant atmosphere, being able to talk about all these different topics. We had over 250 papers touched and 50 at least partially reproduced, so also definitely a success from this reproducibility perspective. To dive a little bit more into what the PhD students worked on, we had 7 plus some sub-projects. We had one team that worked kind of on speedrun reproducibility. We had a team that worked on biomedical segmentation. Students worked on LLM-supported automation of repository setup for reproduction and basically improving the reproducibility assessment that we had before. Easy or a decision support on whether people should try to start reproducing a specific repository or not, just to leave it go or to leave it alone. We had a look at reproducibility cultures across different countries and continents. A team that worked on deep reproduction of pre-trained models and how they can be applied to different data sets. And our hybrid participants worked on different topics, including benchmarking, test time augmentation approaches. And I want to exemplify a couple of these results. So the speedrun reproducibility team, they set themselves a strict deadline of 2 hours per reproduction to get some initial results, some figures reproduced, some numbers basically presented. And the results were quite interesting in a way. So 2 hours is a very tough deadline, and it probably only refers to, or it includes mainly papers where there's nothing that you need to retrain or redevelop. But generally within these 2 hours, at least 26, so around 15% of the papers were reproducible. 30% potentially with some minor issues, where this was just, outside of the time frame. And then 96, so round about 55% were not reproduced within this time frame, and there was no indication that this would be possible within the next minutes or hours. Interestingly, they also dive deeper here into the issues and challenges. Basically here again, this number summarized, reproduced versus not reproduced. With many papers having code available and also having data available, but then many challenges in setting up non-functional conda environments and debugging around conda environments to get things running. This is also the experience of the second team who worked on biomedical segmentations, who also had around 2 hours per reproduction, but slightly less strict, where they looked at basically what information is provided to set up environments and Python environments. There were sometimes textual explanations, requirement.txt files were sometimes present, which we would see as the gold standard or the best practice here. But in many cases, there was also no information present, or it just can't be properly prepared, even though it is provided. Here also looking into this in a little bit more detail. Out of the repositories checked, quite a number, so over 1/3 had actually issues with dependency issues, no really well-defined requirements. packages were defined as dependencies, but then were used in the code, so actually adding to the complexity of installation. But then also the other way around, and with about the same amount, the packages were used but not defined in the requirements. So, lots of challenges in actually getting to set this up. Complementary to this was the work by Andrea, who worked on looking into different cultures of reproducibility. So is the code available? And looking at the affiliation and the country of affiliation of the first and the last author. So important, this is just the institute. We don't have information about the passport or any kind of nationality, but just the institution of the authors based on the institutions. And what you can see here is actually that this seems to be a universal problem. So it's not as if there's one continent that specifically is like extremely good or extremely bad in terms of code sharing. Maybe actually Europe, we could try to be here a little bit better, and great for Australia that they seem to have the lead here, but this seems to be a fairly, ill-balanced picture across the board. So for the first author, okay, maybe let's look rather at the last author. In many cases, these are executive decisions, whether code is published or not, right? But here the picture is, again, pretty much the same. So not very big differences here. And this seems to be a conversation that we need to have across our community, but also where we are starting on equal footing, more or less. Again, Europe, we should, go for more code sharing, ideally, but where we can start the discussion on equal footing and foster here the collaboration. So with these examples, let me summarize the most important insights from our hackathon in 2023. I want to thank our sponsors who supported the hackathon and who made it possible that we have this hackathon the way that we had it. But again, it was really a complex research questions, but the participants that we had were extremely awesome in keeping and changing and adapting to changed requirements and to changed conditions, to adapting their research question in a way that it stayed meaningful throughout these 4 days. It was lots of fun. We had lots of sugar. We had lots of coffee, and this was also important. So I can only recommend doing that for a hackathon, to have as much sugar and coffee as possible. Actually, environments were the main problem. So Python environments were the main hindrance to be more successful in paper reproduction. So this is maybe something that we also should pay more attention to for student projects and similar, but also, of course, for the papers that we publish ourselves. And we had a very interesting combination of meta-research, so this analysis using large language models or this affiliation, but also direct reproducibility of specific papers and projects. And what we identified from these challenges was that master and bachelor students will require probably quite a bit more guidance and will require clearer tasks compared to our PhD student group that we had for this hackathon. All right, so what we plan to do for the hackathon was then to, for the courses was to focus more on individual paper reproductions and to keep the meta research for now a little bit at the side, to then return to it later on. So to stage 2, the university course for students and computers in computer science, AI, data science, and medical engineering, which is currently in progress, both at FAU and the University of Würzburg. We saw that we definitely need more people. And I want to put a big thanks out to Linda, Sophie, Noah, and Anshul, who did a tremendous work throughout the last semester, especially at FAU. They supported the students, they set up evaluation sheets, etc., but did here really quite a lot of work to get this project running. So the setup, we have 2 sites, FAU and University of Würzburg. As I've said before, To summarize our goal, our target audience is master and bachelor students. We want something that is broadly applicable, interesting, and relevant to these study fields. We want to have something where students can adapt to basically the projects to their knowledge level and can develop independently with different levels of expertise and interests. We want to use this as a platform to introduce fundamental research techniques. And ideally, this is the perfect preparation for a thesis, master thesis, bachelor thesis, but also then to start as PhD researchers. We had 3 conferences and challenges that we considered: CVPR 2024, MICAI 2024, and the MyDoc Challenge, where I'm very happy to announce that there will be a 3rd edition, MIDoc 2025, this year, as a small side note. About organization and course curriculum, we had the following idea. We wanted to start to give students a good basis to just understand papers and to understand reproducibility. So each student had to analyze around 50 papers from these conferences to strengthen their ability to read scientific papers and to have a basis for then selecting papers that they want to reproduce. We supported this by a lecture on reproduction theory and reproduction in practice. The students had then the task to put each paper into a reproducibility level category. So -1 or 0, where the paper has not enough information or exceeds computational capabilities. Category 1, where it should be very straightforward to just basically reproduce results that are available in the paper without having to transfer much. Level 2, where some changes are expected to be required. Moderate changes, since code might not be commented or it's not really, the repository is not really set up well. 4, where no code in PyTorch or Python is available, so they have to re-implement and train something pretty much from scratch. And level 5, where there is no code available, so implementation has to be done from scratch and or from pseudocode. So we see this as the highest level complexity. I want to emphasize here this point here. We can't retrain a huge diffusion model, text-to-image model within the context of this course. This would neither be efficient nor interesting, to be honest. So we had here rather strong limitations on the available hardware and infrastructure. So after this initial paper analysis, students had to select papers worth 100 reproducibility points and propose a working plan to reproduce not the full paper, but parts of the results. And here we supported this with lectures on how to use cluster systems and had regular meetings with the student to support their development and to have intermediate reports in case that they needed support throughout the semester. As I've said, we wanted to look at this from a broader scientific development perspective, where students should, towards the end, summarize their results in a structured report. And we wanted to integrate a peer review component as well, so they had to scientifically review the reports from other students. And we also had lectures supporting this for scientific writing and then peer review as a context as well. And finally, presentations, explanation of discussions of the reproduced papers and failures, and with the content and form, of course, dependent on the specific research plan that the students proposed. And here, again, some input on scientific presentations for the students. I know I'm running a little bit late, but I'll try to summarize the main points concisely. So our student cohort was 60 students at FAU, where we said this is the capacity that we have, and 10 to 15 students at the University of Würzburg. 50 students completed the analysis at FAU and 10 at the University of Würzburg. The reproducibility proposals basically were submitted by the same set of students, but what we saw is that we had quite a drop of participation then for the final submissions at FAU, and the submission here at the University of Würzburg is still open, but I'm currently confident that most students will still submit their final results. So this is all preliminary. What you will see on the next slides is very preliminary. I've used all my prompting skills with ChatGPT to get some plots out, but preliminary results, please see it really with this small warning or this disclaimer. So a brief early evaluation of the reproducibility descriptors. We evaluated code availability and quality, required compute and used hardware, or rather the students did, and this reproducibility level, and had almost 1,600 individual papers analyzed, as you can see here, where quite a substantial number had code available, where dependencies were mentioned, where students, at least at first glance, said that the code was well commented and that pre-trained models are available. So rather, I would say positive results in some way. Then we looked at the paper ratings, and we had 880 papers with ratings from 2 students or more. And interestingly, we had an agreement on 231 of these papers, and therefore a disagreement on 650. So it was expected that we have quite a bit of variability here, but this was a little bit more than we expected. And now if we look at the confusion matrix, where we see basically which students, how did the students disagree, they disagreed a lot. So it's also not there is no real systematic. What I would like to highlight here is basically this confusion between 5 and 0, which is basically very, very difficult to reproduce, but possible or not possible to reproduce. So this is not surprising that we have here a confusion. But for the others, I would have liked more, just here off the diagonal, a little bit more of confusion and not that much all over the place. So this seems to be something that is not particularly well defined, or where we maybe want to be more clear about what we expect and how we expect this. So still lots of things that we want to look into, again, with this disclaimer, and we still have to look into the results from Würzburg here. When we look at an early evaluation of reproducibility success, we had 111 papers analyzed in detail by 22 students at FAU, and the evaluation is currently level independent. And what we identified is that there is a strong variability of the number of papers that students reproduced and the report quality. But generally, interestingly, we see here that around 50% of the papers, actually the students were able to reproduce the results with approximately equal numbers that they came up with. 5 to 20%, also about half of the papers were reproduced with results that were 5 to 20% worse. So I would say this is also a little bit to be expected. We had only 4 failed reproductions, and interestingly, 3 papers where the students got better results, and partly substantially better results than reported in the original papers. Some students also did qualitative comparisons, which, for example, in image generation is also completely valid. What we have to keep in mind here, that students also have to deal with success bias. So what we see here probably is also rather the successful reproductions, and we are missing quite a couple of failed reproductions over time. But generally, I would see this also for the students as quite a bit of success that they were able to reproduce that many different papers here. To summarize here, the main points, the lessons that we learned is that we need to provide students with clear structures to support them and to also foster downstream analysis, similar to what you've now seen on the previous slides, but to go more in depth about where did students face challenges and how did the papers and the reproductions differ from each other. We probably will do for any future iteration some kind of LLM-based pre-filtering, although it will be challenging and we will have to consider this in the bigger research question of understanding reproducibility as students' projects. We definitely, for future iterations, also want to, again, encourage projects that go beyond reproduction, for example, as two-stage projects or as follow-up or as theses. And I think what we also like to have is to think about whether we can integrate hackathon-like structures again that foster this initial excitement and ideally also a bit more teamwork in the groups. So maybe this can be something like a kickoff event. What we also aim to do is to integrate the learning of specific tools more strongly into the reproducibility project, but we also still have to balance this with, the input lecture and the actual programming work that they have to do. So what is next? We see this extremely high variability of how students think, whether students think papers have a specific reproducibility level. So what do our large language models or artificial brains think about this? Can this be compared to the variability of students? Can we support them using LLMs? Can they, better understand these tools and these papers using LLMs? We want to understand the connection between the reproducibility level and reproducibility success. And we want to encourage our students to consider contributing to reproducepapers.org. For lessons learned for me specifically, I will definitely work on a student project and thesis checklists and integrate trainings more heavily to have this also established for student projects and theses with me. And I think this is a personal vendetta of Bernhard, Andreas, and me to battle against empty promises and empty repositories and paper rebuttals in papers that promise but don't deliver, and to make sure that we do not have these biases then also in our review procedures. And I'd be super excited to hear your insights, your experiences, to get your input, and to have also contributions from your side. All right, so this is our timeline here, right? We're in the profit stage. I'm super happy that I can present this work here in the data science seminar. At the same time, I think we're not yet quite in this profit stage. There will be a number of repeats. We will have to reproduce these projects. We have to reproduce these hackathons to get more reliable insights and results. And with this, I would like to again thank you very much for your attention in the last minutes, in the last hour, and thank my team, thank the participants of the hackathon. Again, thank Linda, Noah, and Anshul, as well as Bernhard and Andreas for being a great team, my PhD students, funders, and I'm very happy to take questions following this talk. Thank you.
Thanks a lot, Katharina, for the very, very interesting talk. A little bit shocking, a little bit, but also there's light coming up.